In this video, I want to take a look at a pretty interesting three-dimensional solid called Torricelli's trumpet, or sometimes called Gabriel's horn. That might be the more common name. This is an interesting shape because it's going to have an infinite amount of surface area and a finite amount of volume. So let's take a look. This is going to be set up in a pretty typical calculus format. You've likely seen these problems if you've taken a couple of calculus courses. We're going to consider some function, in this case 1 over x, on the interval from 1 to infinity, and we're going to look at this region between the function and the x-axis. Now for us, we are not going to take a look at the area of this region, which is a pretty normal thing to do in calculus. What we're going to do instead is revolve this shape around the x-axis and create some sort of a three-dimensional solid. The way that we're going to do that is by imagining the ghost or the shadow that this region leaves behind as we revolve around the axis. Here's what we've got. We get this kind of bugly trumpet shape, which makes sense when you think about the name of it, Torricelli's trumpet or Gabriel's horn. So the questions are, what's the volume of this horn, and what's the surface area of this thing? Evangelista Torricelli was an Italian physicist and mathematician who was really interested in this kind of thing. He was a student of Galileo. He wasn't alive for very long, but he had a pretty good prime, I would say. He was the inventor of the barometer. He is also one of the first people to give a scientific explanation of the nature of wind, where it comes from, talking about air pressure changing, all that kind of stuff. Most importantly for this video, though, he was baffled by this problem. So let's take a look at the volume of Torricelli's trumpet using a pretty common calculus approach. We're going to use something called the disk method, which isn't a very difficult thing. We're going to imagine some rectangular pieces that are going to approximate our functions. And we're going to revolve these rectangular pieces around the x-axis. Every time we do that, we're going to try and investigate what kind of shape these rectangles create. You'll notice that they create these kind of nice circular little disks, which makes sense when we think about the name of this thing, the disk method. So the way that we're going to do this is we're going to try and find the volume of each of these disks and add all of those volumes up. You can imagine a whole bunch of coins of differing sizes stacked next to each other to try and approximate the shape of this horn. And if we can do that, then we'll get a decent approximation of the volume. Okay, so we need to find the volume of this shape. That's going to be relatively easy if we can find the area of the face of this thing, which is a circle. So we need the area here, and we also need the thickness right here. The thickness we're going to call delta x. It's going to be some interval of x values this wide right here. Once we have the area, which for us is pi r squared, we need to figure out what our radius is. Our radius is going to be the height of this rectangle. And so you'll notice that's just going to be a y value on this curve. So we'll use something called f of x sub k star. Let me write that out, and I'll tell you what that means. We have to pick an x value on each of these things to define the height of our curve. Now that sounds a little strange because the heights are defined by y values, but the height of each of our rectangle is going to be a y value at a specific point. In our case, it looks like I've drawn this with the x values being the leftmost points on each of these rectangles. I could draw a different rectangle where that's not the case. Ooh, let me get a nice straight line here. Something like this, where it looks like the point that I've picked is somewhere in between. This x value would be our x sub k star for the kth rectangle. K is going to be an index counter from 1 up to n, however many rectangles we have. So in general, what we can do is say the volume of the kth disk is pi times f of x sub k star squared times delta x. This is our area of our circle times the thickness of our disk. And then we have a pretty basic slice and sum thing where we can slice this into a whole bunch of disks and we can find the volume. We said that was pi times f of x sub k star squared times delta x. And then we can approximate the total volume of Gabriel's horn by just adding these things together. We'll say pick n number of slices, and this is what they look like then. Oops, I need an approximation sign here. There we go. All right, now the magic of calculus and the definition of the definite integral says that if we look at an infinite number of rectangles, or sometimes people will say delta going to 0, the size of each of our rectangles getting really, really tiny, then what we'll have happen is that this volume will be an exact thing. It's not an approximation of our volume anymore. And by the definition of our definite integral, this turns into an integral from a to b, our starting point to our ending point, of pi, oops, I forgot my stuff here. There we go. Pi times f of x squared dx. You'll notice my x sub k star just turns into an x, and my delta x turns into a differential. So in our case, it's a little bit trickier because this limit of integration is actually 0. What we have is the volume of Gabriel's horn being the integral from 1 to infinity of pi times our function squared dx. So that's our integral from 1 to infinity of pi times 1 over x squared dx. Or we can write it this way. I like to maybe factor the pi out front. There we go. And I've just got 1 over x squared dx. So this is the integral we're going to have to evaluate. We'll have to be a little bit careful about this limit of integration. This is technically an improper integral because we have this infinite width on here. So this is something we'll have to just deal with. Not a big deal though. The way that we're going to do it is by applying a limit as some dummy variable. I like to use t, goes off to infinity. So our volume was pi times the integral from 1 up to infinity. I'm going to say from 1 to t of 1 over x squared dx. So I can really write this as now pi times this limit as t goes to infinity of my integral from 1 to t of 1 over x squared. Or maybe, in fact, I'll just say x to the negative 2. Super easy to anti-differentiate this thing now. We can just use the power rule. So this is pi times our limit as t goes to infinity of x to the negative 1 over negative 1 evaluated from 1 to t. So this is pi times our limit as t goes to infinity of, this is really negative 1 over t plus 1. It's pretty easy to see what happens here. When t goes to infinity on this thing, this whole fraction is going to approach 0 because we have 1 divided by an infinitely large quantity. And so what we really have is pi times 1, or pi. The main result here isn't so much that the volume is specifically pi units cubed, it's that our volume is finite. It's some real number. That's the important part. Now what we'll do is we'll take a look at the surface area of Torricelli's trumpet using a similar kind of method. So we're going to approximate the surface area first by using a whole bunch of frustums. So just like we used a whole bunch of disks earlier, what I'm going to do now is divide this up into a bunch of trapezoids instead of rectangles. And we'll revolve these trapezoids around our axis to get this kind of frustum shape. Now a frustum is really just a portion of a cone. And what we want to do is we want to approximate the surface area of this whole Torricelli's trumpet by looking at the areas of each of these frustums and adding them together. So the areas of our frustums are going to be similar to the area of a cylinder, except instead of a total length here, we're going to use this diagonal length. So for our area, this is what we're going to have. This is going to be 2 pi times, maybe I'll say r average, because it's actually the average radius here, times our length, and that's our diagonal length here. What we mean by the average radius is it's the small radius plus the big radius divided by 2, or what you can think of is it's the radius right in the middle. So for us, we're just going to be careful, and we're going to select our x sub k star right there, and our radius is going to be f of x sub k star. All right, so we've got that this area is going to be 2 times pi times f of x sub k star times this diagonal length. The diagonal length we can use a Pythagorean theorem to get. This is a right triangle, so we'll say this is our delta x. That's a bad delta, but that's the width of this thing here. And this is like delta y. I'll use an absolute value of it just to make sure we're thinking about this as a positive length of a triangle. It's not really going to matter too much because we can hopefully see that our length using the Pythagorean theorem is really the square root of delta x squared plus delta y squared. Whether or not we include the absolute values, we're going to square it and it'll become positive. Then what we can do is do some kind of factoring. And we can say this is delta x times the square root of 1 plus delta y over delta x squared. Then we'll use something called the mean value theorem that says that we can swap this thing out for f prime of x at a specific x value. So maybe what we'll do is say, let's pick f prime of x sub k star, and that'll approximate this slope here. So our length then ends up being a square root of 1 plus f prime of x sub k star squared times delta x. That's the area of the kth frustum that we have. Kind of a messy formula. What we'll be able to see then is that if that's the area of the kth frustum, 2 pi times f of x sub k star times the square root of 1 plus f prime x sub k star squared times delta x, then we can do the same kind of thing that we did before. We can say that our total area is a sum, or approximated by a sum, of n of these things. This is a long formula to write. And then we can apply a limit in the same manner that we did earlier. You could say or delta goes to 0 for this sum. And we've got k equals 1 up to n of 2 pi f of x sub k star, again, times the square root of 1 plus f prime x sub k star squared delta x. And by the definition of a definite integral, this turns into the integral from a to b of 2 pi f of x square root of 1 plus f prime of x squared dx. Now for us, that means that if our function was 1 over x, the derivative is negative 1 over x squared. And so for us, that means our area is going to be the integral from 1 to infinity. We've got this improper integral again. Maybe I'll factor the 2 pi out like I did earlier with the pi. And then I can say this is 1 over x times the square root of 1 plus the derivative squared. So that's really 1 over x to the 4th dx. And now we need to figure out what this thing is. That's a little bit tricky. So if our area was 2 pi times this integral from 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4, you could go ahead and say, well, that's really, if we combine these things together, make this a square root of 1 over x squared and multiply it all out, that's really 2 pi times the integral from 1 to infinity of the square root of 1 over x squared plus 1 over x to the 4 times 1 over x squared, which is 1 over x to the 6th dx. You could add these fractions together, and you could say, well, this is really a square root of, this is x to the 4 over x to the 6. And so this is x to the 4 plus 1 over x to the 6th. And that's all under a square root dx. And then you could say, well, that's 1 to infinity, the square root of x to the 4 plus 1 times 1 over x cubed. That's our square root of 1 over x to the 6th dx. And then you could use integration by parts to go on from there. And oh my goodness, this sounds terrible. Let's not do that. What we could do is just notice that this value is greater than 1 for these x values. For x, maybe I'll do this. For all the x values in between -1 and infinity. No matter what we put in here, we're going to, oh, sorry, not -1, +1 to infinity. No matter what you put in here for x, you're going to have 1 plus a whole bunch of stuff. Whether it's big or small, doesn't really matter. And so the square root of that will be bigger than 1. So what we can notice is that our integral this 1 over x times the square root of 1 plus 1 over x to the 4 is greater than the integral of just 1 over x dx. And this thing we can do. This thing we can say, well, we'll use a limit again to clean up that infinity. And so this is really from 1 up to t of 1 over x dx. Well, that's going to give us 2 pi times, maybe I'll throw the limit out front again, the limit as t goes to infinity of 2 pi times the natural log of t minus the natural log of 1. Notice, though, the natural log of t goes off to infinity as t goes to infinity. And so the problem here is that this is not a finite value. So we just showed finite volume, infinite surface area. Because again, remember, our integral is actually bigger than this infinity. So our area is bigger than some infinite value, meaning it must also be infinite. This is a really cute little comparison to do instead of having to crunch through this nasty integration by parts, which isn't so bad. Feel free to try it on your own if you know how to do integration by parts. All right, so what does this really mean? We have this interesting solid that has a finite volume and an infinite surface area. What was the fallout of this discovery? Well, first off, Torricelli himself wasn't convinced. The story is that he went back to try and show that either the volume was actually infinite or the area was actually finite. This kind of dueling nature of the volumes and areas didn't really satisfy him. I'm not sure if he eventually did convince himself of this or not. He died relatively young of, I believe, typhoid, and so I'm not sure where he landed on this. But I know that at first the rumor is that he wasn't convinced. This inspired a lot of debate about the nature of infinity. Galileo, Hobbes, Wallace were all involved. These are big names in philosophy and mathematics at that time period. This is all pre what we would call calculus. This is before Newton and Leibniz kind of formalized this idea of calculus and put all this together. And so the methods that Torricelli was using here definitely predate what we normally call calculus, but they were essentially this idea of cutting things into smaller sections. This is a pretty important piece of what calculus is, and the problems that were coming up before Newton and Leibniz really formalized everything were mostly around these kinds of ideas, trying to wrangle infinity and figure out what the nature of it was. This kind of almost paradoxical shape or solid was really bewildering at the time. This also inspired something called the painter's paradox, which is essentially this. Since we have a finite volume of this solid and an infinite surface area, you could imagine a painter, and you could say that they could fill this solid with a finite amount of paint. But since they can't ever coat this thing with paint because it's got an infinite surface area, that means that they can fill it with paint but never paint the outside of it itself. And that seems to be a paradoxical thing. So that's kind of a weird, bizarre situation. The converse of this doesn't happen to be true. What that means is that there are no shapes that have a finite surface area but infinite volume, which seems strange because we normally think of volume as this higher dimensional study of size than area. But if the surface area is finite, then essentially that provides an upper bound of the volume. You can flip these formulas, these integral formulas, around pretty nicely and show that the surface area one provides an upper bound to the volume one. And so if that surface area is finite, the volume has to be finite as well. So anyways, this is a interesting solid. It's something that I think every calculus student should see at one point or another. It's one of my favorite little seemingly paradoxical shapes that we get to take a look at in an introductory calculus sequence. I hope you enjoyed it. Let me know if you did, and have a great rest of your day.